Quadratic Functions and Inequalities, the review. So let's start by looking at our outline, and the first thing we did was Peach's perfect pen, and the idea was just the introduction of the quadratic function, which was a parabola whose domain is the set of all real numbers and whose range depends on the direction of opening of the parabola and the position of its vertex. We also used a little bit of technology to calculate a y value given an x value and to calculate an x value given a y value. So those are all graphical methods that you should know to solve this. We then moved on to the quadratic function to define it, talk about vertex form. So let's talk about vertex form. And we know that parabola can open up. We'll have an axis of symmetry which passes through the vertex. The vertex is at the point PQ. The axis of symmetry has an equation of x equals p. The domain is the set of all x such that x belongs to the real numbers. And the range is the set of all y such that y is greater than or equal to q. In this particular case, since it opens up, and would be less than or equal to q if it opened down. We need to know how to graph, to label interesting points. Points of interest would be x-intercepts, the y-intercept, which wouldn't be shown here, but let's change the curve a little. And there's the y-intercept. Always put arrows on the end of the curve to indicate that it goes on forever, unless we're drawing a particular situation, in which case we won't do that, and we will also restrict the domain and the range. Questions that we did involving this were on page 174, and an important part of doing any of this stuff is to take a look in the book and look at page 173 for the key ideas, which define the standard form function of a quadratic equation, which is y equals ax squared plus bx plus c, or in function notation, f of x equals ax squared plus bx plus c, with the proviso, of course, that a cannot be 0 in order for us to have a quadratic, to have the x squared term. B or c could be 0. And it talks about that it opens up if a is greater than 0, it opens down if a is less than 0. The diagrams on page 173 will show all of the relevant information: x-intercepts, y-intercepts, vertex, axis of symmetry, maximum and minimum values. So I urge you, whenever you're doing any review in the book, always take a look at the section where we did the questions, and then look at the key ideas. Okay, look at the page with the key ideas. It should be just before the questions in the book. All right, the next thing we did was the worksheet called Dressing Up y equals x squared. And that was basically doing an exploration of the effect of a. So we know, and we're looking at this form, y equals ax minus p squared plus q. That's the whole idea of dressing up y equals x squared. So let me just move this down, and we'll talk about y equals ax minus p squared plus q and everything about it. So a, that gives us the direction of opening and the vertical stretch. Okay, two things. The absolute value of a is the vertical stretch. If a is 2 or 3 or 4, if it's greater than 1, the curve is stretched vertically by a factor of a, which will result in a vertical expansion, and the curve will be narrower. If a is between 0 and 1, then that's a vertical stretch by a factor of, let's say, 1/2, and that would be a vertical compression. If a is less than 0, if a is negative, then that's a reflection in the x-axis, right? But the very first thing we want to look at is the absolute value of a and describe the stretch. And then after that, we'll look at the sign of a, which will tell us whether the parabola opens up or down. That is, whether there's a reflection in the x-axis or not. P, x minus p, this moves to the right p units, it's a horizontal translation, right p units, and q is a horizontal translation, up q units. So that whole worksheet basically on dressing up y equals x squared. Remember, the order that you do things in our transformations is stretch, reflection, and lastly, translation. And if you're describing those in words, which is very important, you would say vertical stretch. Let's put an actual example in. Y equals -3, x plus 2 squared minus 5. It's a vertical stretch by a factor of 3. By a factor of 3. It's a reflection about the x-axis. Okay, and it's very important that we do this in order. It's a horizontal translation, which way? Left 2 units. And there's also a vertical translation, down 5 units. Okay, so it's important that we are aware of the effects of that, and that's covered off in the worksheets, as well as the worksheet, everything you always wanted to know about quadratic functions, which leads to the exercises on page 157, and that leads us to the key ideas, which are before page 157 on page 156. So one thing you should be reviewing is the key ideas on page 156, which will go over those values of a, x, p, and q. The next worksheet we did was equations of parabolas, and that is given an equation, be able to describe. So for example, what we just did here, given this equation, be able to describe what's happening. Also, what we might want to do is say, let's say I was given the point 3, 9 on y equals x squared. What is its image point? What is its image point? Given the above transformation. So what I'm going to do is I'm going to do that up here. I'm going to start with 3, 9, and I'm going to go through. So vertical stretch by a factor of 3 makes that 3/27. Reflection about the x-axis makes this 3/27. Horizontal translation 2 units to the left makes this 1/27. And then down 5 makes this 1/32. So if you have to describe what happened to a given point, even if it were the point x, y, this would be then x 3y, x -3y, x minus 2 -3y, and x minus 2 -3y minus 5. Right, that would be the tracing out of some general image point. X -3y, x minus 2 -3y, and x minus 2 -3y minus 5. So this is a specific image point, the point 39, running through those transformations. So very important that looking at an equation, you can describe the transformations in words, in order, right? Stretch, reflection, translation, translation. And that you can then take a point and do each of those particular transformations to that point or to a general image point. Next thing we wanted to do was be able to figure out the equation of a parabola given some information, such as a vertex. Okay, so remember in this, I'm just going to move up a little bit here. In the equation, the vertex is at PQ. Right, where P is the number that follows the minus sign, right? And again, think of the transformation. This is x plus 2. That goes left 2. So the P value here will be negative 2, right? I would have to write this as x minus negative 2. And the Q value would be negative 5 in this particular instance here. And that would give us our vertex. So if I give you the vertex, then you know the P and Q values. And generally we give you 1 point on the parabola. That gives you an x and a y. So you would know P and Q and x and y. And that would leave you solving for A. In some cases, we may give you, not give you the Q value, but may give you the P value. And you'll be given 2 xy's and get 2 equations where you have A and Q as the unknowns and have to solve a system of equations. And we did that on the worksheet. We did that on the quiz as well. So you can look through the worksheets. And then there were some questions involving applications of quadratics. We had a cable on a bridge as an example of that. Next step. Next thing we did was convert between standard form and vertex form. Okay, standard to, this would be vertex form to standard form. And the only thing to watch out for here is you keep this in brackets, that you properly square the binomial. Remember, we must get 4 products, which will collect into 3 terms. The easy way to square a binomial, it's the square of the first term. It's the first term times the second, so x times negative 5 is negative 5x doubled, gives you minus 10x plus the square of the last term, and minus 17, and then we multiply this out, minus 30x plus 75 minus 17, and collect terms, 3x squared minus 30x plus 58. And now we want to convert, so let's actually start with 3x squared minus 30x plus 58. And let's run through the way that we convert from standard form to vertex form. Standard form really only gives me the y-intercept, right? You set x to 0, and that gives you the y-intercept of 58. We really want to be able to look at this and describe it. So we do completing the square in a couple of different contexts. One is in the context of a quadratic function like this. And in this case, we need to keep all of the information. We need to know what the vertical stretch is. The other form that we do completing the square, the other time we do completing the square, is to solve a quadratic equation. And in that case, we're only interested in the x-intercept, so we can go through and divide out the 3. Remember, that would be, this is set equal to 0, and I could divide both sides by 3. This is y equals, so we can't do that. So the method is you factor the term in front of the x squared from the x squared and the x term, and leave yourself some space and put a plus 58. So this line is still the same as the line above. I now basically want the binomial form. This is x minus 5 quantity squared. That would give me x squared minus 5x minus another 5x, which is minus 10x plus 25. So we complete the square. That's what we're doing here, is completing the square. Now, did I just add 25? Not really. I added 3 times 25. So I've added 75 to this line. So I'm going to go and subtract 75 from this line. I'll do that out here. And 58 minus 75 is minus 17. So it's not a surprise that we got this. That's what we wanted to end up with. But in this form of completing the square, converting from standard form to vertex form, we have to retain that 3, right? We need to know this opens up and that it is vertically stretched by a factor of 3. It will be narrower, that the vertex, right? So we need to be able to describe stuff about this. It opens up. It's got a vertical stretch by a factor of 3. There is no reflection. There's a horizontal translation. This x minus 5 says go right 5. So it's a horizontal translation, right 5 units. There's a vertical translation, down 17. That puts my vertex at 5, negative 17. My axis of symmetry, the equation of that is x equals 5, right? That's x equals p. And so that takes care of our A, our P, and our Q, and allows us to describe, right? Vertex form allows us to make a description. So given the standard form, we convert to vertex form, which allows us to then give a description of this quadratic function. That's converting. That's on page 192. Is the questions, and that actually has the key ideas are also on page 192, and that again shows you how to do that. And I urge you to look through each section, look at the timeline for quadratic functions. If you've lost it, it's on Schoology, and take a look at each of the sections where stuff is assigned, and take a look at each of the key ideas. The next step up is to find out what kind of situations are described by quadratic functions. Okay, here's page 196, number 22. This is an area problem, so we do area problems, we do revenue problems. You kind of need to review a little bit of each. Let's fill this in. Let's label everything else. There will be an x here, and an x here, and this side, and this side. And this will be a y, and a y, and a y. And this will be 3 y's from here to here. So I have a total of 1, 2, 3, 4, 5, 6 x's. And I have 3y, 4, 5, 6, 7, 8, 9. And I have a total of 9 y's. And that's going to give me my 900 meters of fencing. And can we simplify this at all? Well, we can divide through by 3, 2x plus 3, 300. 6 divided by 3 is 2, 9 divided by 3 is 3, 900. And my area is 3y by 2x, and that's kind of handy because I can solve that. So let's call this 2x times 3y, and we can go up here and let's solve for 3y. It'll be 300 minus 2x. Now this saves me from having to solve for y and getting 100 minus 2/3 x and then having fractions and all of that good stuff in there, since I need the expression 3y and I can solve for that. So area, 2x and 3y. Instead of 3y, we write 300 minus 2x. Okay, this is a quadratic function. We're trying to maximize or minimize. This will be 600x minus 4x squared. So we are actually maximizing because this will open down. Let's rewrite this. Okay, now I don't get to arbitrarily change signs here, right? This is not equal to 0. I can't divide out the negative 4. So now we do have to divide out the negative 4, but we keep it. That gives me x squared minus 150x. Leave some space. There is negative 4x, half of 150 with this sign, right? So minus 75 squared. And 75 squared is 56625. So did I just add 5625? No. I added, actually I didn't add, I subtracted 4 times, negative 4 times 5625 is what was added. So that's subtracting 22,500. If I multiply this out, I'll get negative 4x squared. I'll get plus 600x. That's the same as up here. But then I will get minus 22,500. So we have to add 22,500. And this tells me that I will have a maximum area of 22,500 when x is 75. So a maximum area of 22,500 when x equals 75, which means y, let's go back up here, 3y is 300 minus 2 times 75. 3y is 150, y is equal to 50. So when x equals 75 and y equals 50. That makes the large pen here 3y, 150, by 75. Okay, so the large pen is 150 by 75 meters. And the 3 smaller pens, 3 smaller pens are each x by y. They're each 75 meters by 50 meters. Okay, and so if we were to multiply that out, 150 times 75 is 11,250, 11250. And 3 of these guys would also be another 11250, which would add up to 22,500, which is our maximum area. Okay, so that is solving an application problem of a quadratic function. Okay, you should look through the other ones as well. There's some on the worksheets, revenue problems and number problems. And that's on the worksheet called What Kind of Situations Are Described by Quadratic Functions. Take a look at that one again, just to make sure that you're able to run through the steps for solving these. Okay, the next thing we did, and now for something almost completely different, is graphing linear inequalities in 2 variables. Okay, so graphing linear inequalities in 2 variables, you'll remember we did a worksheet on this. And the idea really is to graph the linear equation. That's an equation in x and y, right? A straight line. So it could be something like 3x plus 2y equals 12. And that can be graphed by putting this into slope-intercept form. Right, so it would be 2y is negative 3x plus 12, and y is negative 3/2 x plus 6. So find the y-intercept at positive 6 and use the slope to go down 3, right 2, keep going down 3, right 2, or go up 3 and then go left 2 to find other points. You can also graph this by finding the intercepts to find the x-intercept, set y equal to 0. That'll give you 3x equals 12, so x is 4. And to find the y-intercept, you set x equal to 0. That gives you 2y equals 12, and y is equal to 6. So either way, you want to be able to graph a linear or a straight line. And what we are doing is a linear inequality, which means what we're going to be doing is graphing a straight line. Let's say we do this one at 4 and 6. And we're going to graph this line, and we're going to shade a region, and it'll be either the region above the line or the region below the line, depending on the inequality. So if I said that 3x plus 2y is less than 12, then you would graph this line, and in this case with the intercepts, use a dashed line because it's strictly less than. Since 3x plus 2y is less than 12, well, we have to figure out, is the point 0, 0 a test point in the region? If I put 0, 0 in for x and y, this will be 0, which is less than 12. So given that that's the point, then from there we can shade below the graph. Okay, we could also rearrange to get 2y is less than negative 3x plus 12, and y is less than negative 3 halves x plus 6. And this is the line that we graphed, negative 3 halves x plus 6. So when it's in this form, the inequality y is less than, then we know for sure that we are shading below. When it's in this form, then we need to use a test point. And I generally use the test point 0, 0. If 0, 0 makes this true, then 0, 0 is in the region of solution and you would shade below. If 0, 0 were to make this false, it would not be in the region of solution and you would shade the other part, or shade above. And that's sort of the general idea with the linear inequality in two variables. And that questions for that are on page 472, meaning the key ideas are on 471. And again, they talk about the inequality symbol. And if this symbol, lost my pen, if the symbol were less than or equal to, then this would become a solid line, again with arrows on both ends, since the line would now be part of the inequality, it would be part of the solution. Okay, the second thing we did was quadratic inequalities in two variables. Questions are on page 496, meaning the key ideas are on 496 as well. And a quadratic inequality in two variables will be a quadratic region. So in this case, it will be a parabola, and we can draw that using the methods that we know from this unit, basically to draw a parabola. And so let's say I want to, and we can also use graphing technology, right? But let's say I want to graph y is less than negative 2x minus 1 squared minus 5. So I would graph this. It opens down. It's vertically stretched by a factor of 2. The vertex is at positive 1, negative 5. So it's there, 1, negative 5. It opens down. It's narrow. Since this is strictly less than, then I'm going to draw a dashed line. And again, we're going to split the region into two areas. And the region is either what's in here and what's above. So in this case, y needs to be less than. All of our y values need to be smaller than this. So we will be shading in between here. Right. And again, I could test this with a test point. I could put 0, 0, 0 and see if this is true. Is 0 less than negative 2, 0 minus 1 squared minus 5? Is 0 less than negative 1? This would be negative 2 minus 5. Is 0 less than negative 7? And the answer is no, it's not. So the point 0, 0 is not in the region of solution, and therefore the region of solution is in between, down here, underneath the quadratic curve. So this is a quadratic inequality in two variables. And the key points, again, the key ideas are on page 496. So important stuff. Look through the key ideas for each section. Go through your worksheets, go through your quizzes, go through your tests, take a look, see what types of questions are being asked, especially on the worksheets and the tests, and also the types of questions in the book as well. And that should get you ready for quadratic functions and inequalities, and I'll have another review for quadratic equations and inequalities. But we'll keep that separate because this has gone on long enough.